All right, guys. So we'll be looking at probability distributions tonight, and we're going to be extending some of the ideas we've studied so far. We'll be extending them now, but we'll be dealing with distribution functions that map outcomes or values of outcomes to various values in a random variable. So all these ideas, like what a random variable is, what probability distributions are, we'll be looking at them one after the other. Before I get started, I would like to ask two questions. You can tell me what a data distribution is, and then you can also tell me what a probability distribution is. What do you understand by data distribution, and what do you understand by probability distribution? You don't have to be correct, just tell me what you think about it before we start.
Hello.
Okay, Mr. Christian, go ahead.
Okay, I'll just talk about data distribution.
All right.
Okay, for my understanding, data can be either normally distributed or skewed.
Okay.
So when data is normally distributed, the thing has a bell shape. Is it a bell curve or bell shape?
Yeah, both are correct.
So, but when it's skewed, it's either skewed to the right or skewed to the left. So that's what I know about
Okay,
data.
that's a very good one. I even like the fact that you went into the visual visual perspective about it, because you can easily, when you tell me something is random, I can just easily picture a bell curve, and okay, this is what the distribution looks like. So yes, that's a very good one. Thank you very much for that. So any other person who wants to tell us about probability distributions? Who's going to try? So are you with us?
Yes,
Okay,
good evening.
since all right, good evening.
Hello?
I can't hear anything.
Oh, okay, so what is probability distribution?
Yes, I'm asking what you understand by a probability distribution.
Okay, okay. What I understand by probability is the likelihood of an expected outcome. So I don't know. So and it can only be between 0 and 1. I think that's what I know a probability is. Um,
Okay, that's a good one. You have treated one part of the problem. So the remaining part is the distribution part.
yes.
Okay, let me move the question
Go ahead.
to hello. Let me move the question to um Andile. Oh no, let me not ask you yet. I'm going to ask Ebube, and then from Ebube I'll go to Anisat and um Queen. Is Victoria with us? If she's with us, then I'll take a response too. So Anisat, can you go ahead? What do you understand when you hear a term like probability distribution? What do you understand by that? Are you with us? Okay, let me go to Ebube. Can everybody hear us? Why is everyone quiet? People are always quiet in their classes. Can Victoria hear us now?
Yes, I can hear you now.
Okay, so what do you understand by a probability distribution? Any ideas? Are you with us, Victoria? Okay, but you can hear me now. Can you go ahead and answer the question? I just want to
Which question?
sample understanding of the concepts before I proceed. Victoria, the question is, what do you understand by a probability distribution?
I've not really time to study, but I know that it's something that a lot of data scientists use. It's part of the statistics um, aspect of data science, and I think maybe it has to do with these normal distributions and all these graphs and things.
Okay, so all these various types of distributions,
Yes.
like the normal, exponential,
Yeah.
binomial distribution. Okay, is everybody responding? I can see your mic is on, but I can't hear anything.
Okay, I think probability distribution is just
Yeah,
that statistical functions that actually show the likelihood, the possibility of getting a particular set of values, as in possible values from a random variable, just like in normal distribution now. When you look at
yeah, go ahead.
just like a normal distribution, when you look at they will tell you this thing is normally distributed and they give you some values. Like what you're doing is it's not, I don't think is, and they have example of the distributions. I know they have normal, they have poison, or is it what I don't know.
Poison.
So but the essence of this is that you get to know the spread. Like a normal distribution, you know what it looks like. Is a bell shape, and that
Oh,
within that particular bell shows you the range of values, and then the probability helps you to go, okay, this is the possibility of getting a particular range of values, or the spread is actually deals with the spread, and the distribution is what I think what helps to determine the possible values or the possibility of getting a particular set of values. That's my own understanding.
you have not given us the understanding. You are giving us a lecture. So, yeah, you hit the nail on the head. Um, the first thing that you mentioned, which is very accurate, is the fact that the probability distribution is a statistical function. All right, but without us going into ideas like functions, um, you know, other things you mentioned. In fact, you described a data distribution and a probability distribution together. The only difference between a data distribution and a probability distribution is that a data distribution is the distribution of observed data. All right, so data that has been collected and is being observed. When we check the distribution of maybe each variables in the data, all right, so we can simply just list out all the values in that particular variable. So a set of all the values in the variable is your data distribution
Okay.
for that variable. So you can look at the range, you can interpret the mean, you can calculate summary statistics from that distribution, and then of course you can visualize the distribution to check the variance, the spread, the central tendency, the skewness of the data, like Christian mentioned. You know whether, okay, is it asymmetric to the right or asymmetric to the left? Okay, so you can check all those things like that. Those are data distributions. Now, when we come to probability distributions, all of these are described except two things. One, the fact that we're not looking at observed data, right? We are looking at experimental data. Okay, of course, in most cases, we are looking at experimental data, and we are looking at the outcomes of running those experiments. For example, you pick up your phone. We'll look at this in one of the examples. You pick up your phone. You want to call customer care for MTN or Glo. All right. So at that moment, it's experimental because we don't know what the outcome is. So it's probabilistic. All right. We know that either you will be transferred immediately to an agent or you'll be put on hold. So if you're transferred to an agent, it's a success. If you are put on hold, it's a fail. That is the outcome of that, event, of those events can either be a success or a fail. Okay, so if we just take data like this, data that includes outcomes that are not known, and then we look at what the possible outcomes would be, those possible outcomes make up your probability distribution. So, and those possible outcomes are usually part of what you call a random variable. Okay, so we look at what random variable is. So they're not like your normal observed variables where in your data that you collected, you have variables like price, educational status, city, salary, all those kind of variables of observed data. What you're having in a random variable, okay, is a set of values of random outcomes that we only know that they can take one of many possible values, but we don't know the exact values that they will take. If we know the exact values, it's no longer a random variable. All right. So the first difference is we are dealing with random outcomes. Then the second difference is that attached to each random outcome of those events in the random variable, all right, attached to each of them is a probability. So a set of all these random outcomes and their respective probabilities make up what you call a probability distribution. So unlike in your observed data, let's say you take the salaries column and you're looking at the distribution, each record in that column only has one value, is it not? $60,000, $120,000, 59,000, 97,000. For each individual record in that data is just one. There's just one observed data for each record or each example in the data. So, but in probability distribution, row one would be a random outcome and the probability that random outcome would occur. Okay, row two, a random outcome and probability. So all the rows in your data, when you take the combination of the outcome and the probability for that outcome, a set of all these, double, what's it called? A set of all these two tuples. For those of you that are already now familiar with what a two tuple is, a two tuple means a set with just two values. So that entire set of a random variable, each member in that set is also a set of two numbers. So each row is a set of two numbers. So your distribution, this data distribution, okay, is known as a probability distribution because a probability has been assigned to each of the outcomes that we have. So I hope that makes sense.
Yes.
Okay, so let's quickly proceed to. Oh, I'm quite far away from home, so let's. All right. Okay, I'm still not there. Okay. What is going on here? All right. Okay. So let's proceed. We start with the concept of a random variable. I'll just be keeping this worksheet at the side so that if we need to do anything here, as time permits, we'll also do some examples in Python. Okay, but I want to just introduce the concepts first before we then begin to look at, more intricate details. So the first thing is that a random variable is a numerical quantity that associates a numerical value with each possible random outcome. What we are simply saying here is that, you can have a table. I think I explained this in one of our lectures previously, but I'll still explain it again. So you can have a table like this. Okay, we can actually add more rows to this table. So you can insert more rows. So this is your random outcome. Before I do that, I need to set the distribution. So we have this column which is the outcome, and we have this column which is the probability. All right. So each these two columns, all right, together make up a random variable. We may never put them into separate columns. We can actually attach them. Okay. So you have, let's say, the event that a sale of 2,000, okay, will be made. When we're talking about these random outcomes, okay, we're trying to make probabilistic inference, not on observed data. We're trying to deduce, some insights based on certain estimates. So it's okay. What if on this particular day we have a sale of 2,000? Then we'll not check the likelihood of that sale. Very likely we'll be, getting a likelihood based on a frequencies perspective, where we have looked at historical data, and over time, okay, we've been able to, arrive at a very specific number, probability number. I've explained how frequencies probabilities work, or frequency statistics, right? So if you throw a die, the probability of getting a 5 is 1/6. Okay, but if you throw that die 6 times, you may not even get a 5 once. You may not get a 5 once. So does that mean the probability is 0/6? No. We need to throw it repeated times so that over time we'll calculate the number of times we get a 5. Eventually, let's say we do 600 times. Eventually, we'll likely be having something very close to 100 or slightly more than 100. And when you check the probability, 100 divided by 600 gives you 1/6. So is that relative frequency, the repeated number of trials to get the relative frequency that converges to a specific value that we can now confidently say is the probability of occurrence of that outcome, right? So there are some outcomes that, of course, you cannot experiment to repeat. So you would have to, for example, in the Bayesian approach, you would have to assign probabilities based on degree of belief. But let's say you already have data for maybe sales data in a retail use case. Okay, you check, okay, all the times we had 2,000 sales of $2,000, what's the probability that we got those sales? Or the probability of making those sales, you then come up with a number, 0.7. You do that for the, so we are, all these elements here are not part of the observed data. We now want to look at, okay, what if in the future we want to make inference about what our sales will look like? Let us experiment, all right? So we are going to have a number of trials. We would write out so many sales that we are hoping to get. Of course, we also try to include some worst case scenarios also, like low sales, just to make the data identically distributed. Okay, then we can have different types of outcomes, but then there's a probability for each of them, and so on and so forth. We feel it's stable. Okay, so this is experimental table. A random variable now can be something like, let me try to duplicate this. Okay, this one doesn't work. So a random variable will just totally take off this column. All right. So we can have random variable sales. Now, each value in this column on this data, this experimental data, will then be a tuple. All right. So 2000, 0.7. In other words, to each sales outcome in that experiment, we are assigning a probability. People underestimate probability. They will say, "What do we need to carry out all these experiments?" But you cannot make a decision under uncertainty without bringing in probabilistic modeling, which means you're going to model a number of possible future outcomes. You try to model as many as you can. So this is going to be 500, 0.6, and and so on for each of those records. So to each sale, the probability is assigned. All right, but it will be such that for all the experiments we have in this, in this the numbers here, this entire column or the sales data is a random variable. All the sets or all the events that make up this random variable are called, all the events that are found in this random variable make up what you call a probability distribution. All right, so then the total probabilities in this set is going to be 1. So of course, your probabilities will be having small numbers, because you should be expecting that when you add all the experiments, all the outcomes, probabilities of all the outcomes, you get a total probability of 1. So the total probability, sorry, the total probability of the of this distribution is 1. Is going to be 1. All right. So this pretty much what you have as a random variable. All right. Random outcomes and the probability of occurrence of those random outcomes. We're going to introduce some notation. Okay. The reason we're introducing this notation, don't be scared of this equation. Not this equation, this expression. It's not an equation. So we're introducing it because I want you guys to get comfortable with some mathematical notations. We don't need to go too far into putting a lot of mathematics in what we're doing. There's a lot of mathematical expressions in what we're doing, but at least notations like this, you should know what they mean. Expressions like this, you should know what they mean. So by looking at this, is anyone here who can just tell me how to read this expression? Or can someone just read it out? All right. I'm not asking because I expect you would already know it, but I just want to, sample if there's anyone who has an idea. Probably if there's anyone who even knows who even knows all these things, who is familiar with these expressions. Any ideas?
Yeah, but I've forgotten actually.
Okay. Olawale says he has forgotten. Some things you study in school, you're in the university, you're studying some things. By the time you're done, you just feel, no, this was a body. Let me just throw it away. Let's focus on on practical stuff until you come back to data science and those things come back to your life, like distant relatives. All right, guys. So she says, a message says the symbol after the F looks like Holmes' lost symbol. Yeah, definitely. This is a Greek letter, the 24th alphabet in the 24th letter in the Greek alphabet. That's omega. Of course, the first letter in the Greek alphabet is alpha. So this is capital omega. In statistics, especially when we're dealing with probabilities, we use omega to represent our sample space. I have no idea why the choice of omega, but I suspect it's because when you say alpha and omega is like everything. So it's okay. You know what? Alpha. No, let's not use alpha. Let's use omega to represent everything. So your sample space is this, but we distinguish it from the sample space of observed data. Generally, in observed data, we just use S to represent your sample space. Although in earlier lectures on probability, if you notice, I've been using S to represent the sample space, but omega simply means the sample space. So what about this R here? What does R here mean? I can remember I've mentioned this when we did the linear algebra. Linear algebra, when we did calculus, I remember mentioning this. Any ideas? All right.
Real numbers.
Okay, Miriam, you said what?
I'm not sure. Real numbers.
Yes, real numbers. So when you see just R like this, what does it mean? Real numbers in what space? Is it real numbers in three-dimensional space, two-dimensional space, four-dimensional space? Or is it a generalization of real numbers in all spaces? Is it a generalization or is there a specific space where you talk about this?
I think
I don't know
all
if my question is
spaces,
understood. Okay, go ahead.
like general. I think it's general.
Is what?
Not sure. I think it's general.
General. Okay, so the R there is for one-dimensional space. So look at this. For a 2D space, what we'll be having instead, right? What we'll be having instead for a 2D space will be R2, stands for two-dimensional. So something like this, R2. So this is a two-dimensional space, which means we are stacking two one-dimensional spaces together. So a one-dimensional space is simply R, just R. And this is called the real line. Okay, so what this means is we are trying to associate numbers which obviously come from the real line to elements in the sample space. I'm still going to read what this is. When I say a real line, don't think too far. Think of the numbers you're familiar with, decimals and integers, fractions and negative numbers. All numbers from negative infinity to positive infinity with zero in between make up the real line. So the real line is your one-dimensional real space or one-dimensional space of real numbers. The reason it's called a space and not a set is because it's a set that has a notion of distance measurement. So you can measure the distance between 1 and 4. We know that the distance between 1 and 4 is 3. The distance between 1 and negative 4 is 5. All distances are positive. So any set that has been embedded with a metric or a distance measure is called a metric space or a space. So as not to further confuse anyone. So this is your one-dimensional real space or a space of real numbers. But because it's one-dimensional, we just call it the number line. A two-dimensional R space is a plane. So think of when you draw a rectangle. Any plane shape at all that you can draw, whether it's a circle, a rectangle, uh, um, any plane shape you can draw, okay, can take all values in that real space. All right, so how do we read this? We read this as the random variable x, because we're talking about random variables here. I'm saying the numerical quantity. So this numerical quantity, let's represent it by x. We're going to represent it by capital X so that you don't confuse it for a general variable. So that when you see capital X, you know that, okay, we're talking about random variables here. If you see capital Y, another random variable, capital Z, another random variable. Of course, these are just notations. If you want to, do something tomorrow, maybe you want to write a book, and you decide, I'm not going to use all these notations. Let me start now from scratch. You just define it. All you just need to do is to predefine the notations you want to use. But the problem is that you're going to have a challenge with people adopting the book because they will not be familiar with the notations you're introducing. So let's use familiar notations. Let's use capital letters, especially the well-known letters in mathematics, X, Y, Z. If we run out of letters, of course, the next bet is P, Q, R. And if we run out of letters again, I think we'll just come to ABC. So now we'll read this as X such that sample space maps to R. So so that um, just so that we don't get too confused by all that, let us deconstruct it. All right. So I'll put this here, and I'll tell you. So X, I'm going to write out the spelling for that. I mean the statement for that. X such that um, omega maps to R. Of course, I'm going to introduce those symbols here. Let me just paste, then remove this, such that that doesn't look good. Just a second. I'm going to fix this. Okay. So X such that omega maps to R. Probably would have been better. It would have just been a lot easier if I took the symbols directly. So this is pretty much what that reads as. When we write that symbolic expression, pretty much is what it means. X such that omega maps to R. So what that means is the variable X for which this sample space maps to the real line, which means for each element in the sample space, associate numbers. And if we're dealing with probabilities, it means associate probabilities coming from the real line. Obviously, all probabilities, are found on the set of real numbers. But the interval you're going to find the probabilities, okay? You're going to find probabilities not on the entire real line. So we don't need all the numbers from the real line. We just need these numbers. We just need numbers between, or let me say numbers in the interval 0 to 1. This is an element of R. All right. Yeah, just give me a second. Let me finish this up, then I explain. Okay. So for probability, we're interested in this interval. I need you to be very careful when we write something like this. In the morning, we looked at something like this, 0, 1. Was it not in the morning we did something like this? All right. This set here is different from this set. This set means numbers that are either, this set means there are only two numbers here, or two elements, the elements 0 and 1. But this set here, okay, this set here, this one, it means the interval between 0 and 1. 0 and 1 being excluded. I don't know if that makes sense. A probability cannot be 0, probability cannot be 1. We need numbers in between. So this is the interval to define. If 1 is going to be part of it, we do like this, which means the interval between 0 and 1 is 0 excluded, but 1 included. This is called an open-closed interval. So the previous case we had is an open interval. Open because we're not going to be taking the values of 0 and 1. We'll just take all the decimal values between 0 and 1. So the interval only considers numbers between 0 and 1. Of course, decimals. All right, so this other one is the bracket here is open, the bracket is closed, which means it includes 1. So open closed interval. All right, but we can have the closed open interval, which means give me 0 but exclude 1, then take all the numbers less than 1. We can also write this whole notation in a very interestingly in another interesting way, where we use less than symbols. I don't know if some of us are familiar with stuff like something like this. So 0 less than x less than 1. This is the closed interval, which is this. The open interval, sorry, which means x is going to be bigger than 0. All the possible values of x will be less than 1. They will be in between 1 or 0 and 1. Okay, then if we have this open interval, this closed open interval, it means this is going to change to less than or equal to. Let me see if I can do that here. All right, so less than or equal to, which means we are going to include x. So x can be greater than 0, but x can also take the value 0. All right, so this is closed open. If we have a completely closed interval, it means it's going to include 0 and 1. So the interval from 0 to 1 with all numbers in between is what we're considering when we look at this. So when we use square brackets and put numbers inside the square brackets, or when you use curved brackets, we are dealing with intervals. But when we use curly brackets, we are dealing with sets of numbers. This is also a set of numbers, but it's a set of numbers that falls within a range. This one is a set of numbers that just includes those values we have here. This is just 0 and 1, only 2 elements. This one, how many elements are we going to have in this interval? Can someone tell me? How many elements can we have in this interval? Let me increase this. Anyone? This interval from 0 to 1. So of course here, this interval will be this, less than or equal to x, less than or equal to 1. I don't know if you guys are with me, or I'm already
I think
introducing some abstract stuff here. Okay, Victoria, go ahead.
I think infinite number. So any number from 0 to 1, like 0.01, 0.00, blah blah blah,
Until
up to 1.
exactly,
Okay.
it's going to play. It's going to be plenty
Yes.
now. It's as well.
Yes. It's going to be infinitely many values. You can't count. This one alone is as infinite
Yeah,
as all the numbers on the real line. It's very funny because by the time you check this interval,
epsilon.
okay, the infinitude is just as big as this one. You can't count the numbers here. But look at this one that's even worse when it comes to number of elements. You also can't count. So this one takes infinitely many numbers of values, but this one takes only two numbers, 0 and 1. So this set here or this interval is represented by this. Or what we're interested in when we're talking about probability is the open interval from 0 to 1. And this open interval falls, in the set of real numbers. That is, it's a member, is an element of this set. So a set that's an element of a bigger set, the real line. Okay, so what we're simply saying here is that a random variable can take in, can associate any number on the real line. So this sample space. But if we're dealing with probability numbers, it's not just going to be any number, it's not going to be this number specifically. All right, a random variable, the number assigned to a random variable, just like we looked at here, does not need to be a probability. It can be any number. All right, but when we're dealing with probability distributions, the number, of course, we're going to assign to the random variable clearly is going to be numbers between 0 and 1. All right, so which means if we want to define a random variable from a probabilistic case, we can just change this to the interval from 0 to 1. Always remember, when you see the curved bracket like this and numbers in between, we're not dealing with a set of two numbers, 0 and 1. We're dealing with an interval of numbers between 0 and 1. And there are infinitely many numbers. All right, so let's come back to R, which is what we're really talking about. So X, such that the sample space maps to R, all right, or X, such that the sample space is associated, values from R, values from the real line, which means numbers, all right, numbers, integers, decimals, any of those numbers. Your sample space can take in any of those numbers. No. The sample space is a set of elements. The sample space could be the set. Let's come down a bit. The sample space could be the set of numbers like 5, 7, 9, 0, 11, and so on. So this is what your sample space can look like as a set. Just a second. All right, so we'll put this as a set in curly brackets. This is your sample space, or this could be your sample space. All right, so it contains elements on its own. Okay, now a function that can assign elements to each of the numbers here will be called a random variable. So let's say we have something like, from this R now, we want to consider a specific number of elements for each of these random variables. 1, 2, 3, 4, 5, 6, 7. So we can have another set like 0.1. I don't want to use probability numbers. So let me just use large numbers, or numbers greater than 1. So we can have, let's even just have something like 1, 2, 3, 4, 5, 6. Okay, so 1, 2, 3, 4, 5, 6. Actually, we have 7 elements there, so this is going to be 7. Okay, now you have a set which belongs to this real line. Okay, now any function that can map each of these values or associate each of these values to each of the elements, that is, associate each of the values to corresponding elements in the sample space, all right, such a function that can do that is called a random variable, which means a random variable is a function that can force you to have a set of numbers like 5, 1. I'm going to loosely use the notion of set there by putting this in curved brackets. So please, that's a set of two numbers, or a tuple of two numbers. So I'm dealing with a tuple there. And when we're dealing with tuples, we just use curved brackets. So sometimes the context tells you whether the curved brackets is a tuple or an interval. So the context of the problem will tell you this is 7,2. All right. Let me just do this in advance. All right. So 5,3, we have that here. 9,4, we have that there. 0,5, 11,6, and 90,7. So a random variable that can do this joining for you is called a function that can do this joining for you is called a random variable. I hope that makes sense.
Yeah.
All right. So a random variable would associate probabilities to corresponding values in the sample space. So all that we've been trying to explain with this notation is simply, to achieve something like this. So X is defined such that the sample space maps to R, which means for each element in the sample space, okay, associate with it any number from or any number within R. All right, so that's basically what this notation means. All right, moving on. So variable, because of course different numerical values are possible. Okay, so you can have different numerical values, so it's called a variable, because you're not going to have single specific values. Then it's random because the observed value depends on which of the possible outcomes you can have. These are experimental stuff we're working with. We're working with experimental data. Okay, so the value you're going to get from that, the value of the outcomes can, you do not expect, how would I put this? It's like, it just depends on which of the possible outcomes, results. So it could be any possible outcome. You might not know it from beforehand. All right. Some of these experiments we're talking about might not even be like this experiment here. They might not necessarily be you trying to just specify the values yourself. You can maybe write a program that randomly throws up all these values, or randomly outputs all these values. So it's random. It's not something that you can think of from the onset. So the experiments are like, are random experiments. They're not things you have control over. So since they can take any possible values or any possible results, we call them random. So they are not deterministic. So for example here, this is an example of a mapping from sample space to R. So this is sample space, and this is an interval on the real line. This interval is interval from -2 to 2. You can actually assume this is a closed interval. So which means what X is doing is mapping values in the sample space to the interval, to the closed interval, -2, 2. Because you can take up any value between -2 and 2. You can just randomly assign, so you don't have control of, okay, which one are we assigning? You can just randomly assign any of these numbers. You can take integer values, you can take decimals, and you can decide what will be assigned to those events or outcomes in the sample space. So this is, what X is doing here. What this random variable is doing is associating each element, um, um, associating elements in the interval here to elements in the sample space. And the whole thing is random, so random variable. Too much time I've spent on that. So let me give this example. I talked about this earlier, but let me just now formally bring that up here. So your customer calls a product help desk. Let's say for a particular product, this customer calls the help desk for technical support. So if she's immediately able to speak to an agent, the event is a success S, but if placed on hold, the event is a failure. So the sample space here is the sets S, F, which means elements in the sample space are only two. They can either be a success or a failure, nothing more, nothing less. If it's not a success, it's a failure. If it's not a failure, it's a success. Okay, we're going to see later that this is called a Bernoulli trial. All right, now we can define, that is not well put. Sorry about that. So we can define a random variable x such that the sample space maps to 0, 1. Of course, here we need to now make sure that the set is just two elements, so that each of the elements in this set will be mapped to corresponding values in the sample space. So when you have a success, okay, the x of s, okay, that is the part of this variable where you have a success is 1, and then the part of the variable where you have a failure is 0. The values here is this and this make up the set you're dealing with here. All right, and then the value, the elements that the variable depends on make up what you have in the sample space. I hope that makes sense. So there's so many ways or so many examples we can give for that. So if there's a success and the variable assigns 1 to that element, there's a failure, or the variable tells you that, okay, this is a success. So what is the value for a success? You have 1. So associated to a success is 1. Then if the event is a failure, then the value of that event is a 0. So your random variable is associating values to elements in the sample space. That's basically what we're doing here. All right, so we have two types of variables. We have discrete variables, two types of random variables, discrete random variables, and continuous random variables. Actually, we also have two types of variables in general, discrete and continuous. So if the random variable just consists only a finite number of possible values, then it's a random variable, which means we can count the elements here, right? And they always take counting values like 5, 7, 8. They don't take decimal values unless maybe we discretize a set of numbers and we have decimals, but they're going to be discrete. All right, so they are not going to be continuous. We can actually have a discrete count like 0.1, 0.2, 0.5, depending on what we're working with, but it's going to be within a range of countable numbers. So instead of having an interval like between 0.1 and 0.5, we'd have a set from 0.1 to 0.5 in steps of 0.1. What I mean by that is this. So you can have decimals that will take up values like 0.1, 0.2, 0.3, 0.4, and 0.5. All right, so this is going to be the variable for this is going to be a discrete variable, but you can't have something like this and call it a discrete variable. So what is common between the two? This one takes infinite values between 0.1 and 0.5. This one takes finite values or countable values between 0.1 and 0.5, and they're discretized in steps of 0.1, which means add 0.1 to this, you get this. Add 0.1 to this, you get that. Add 0.1 to that, you get this. So it's discrete. We can achieve that just by counting. Hope that makes sense. So let's move on. I'm going to be very, oh God, I need to be very careful here so that you guys capture what this means. So this is going to be a little technical, but I'm going to explain it, of course. my gen is. Sorry, guys, just give me a second. So sorry about that. All right. Sorry, Messi. I just saw in the comments now. I don't understand. What? Don't you understand?
You've gone past it. Like, I've used my incentive to understand.
Okay. So you have to check specifically. Keep checking comments to know what anyone is saying. All right. So I mentioned that your random variable, okay, can take a finite set of numbers. Even if you have decimals, they must be finite, which means they must be countable. They must be discrete. If this was continuous, we'd have an uncountable set between 0.1 and 0.5. Even between 0.1 and 0.11 alone, we have uncountable numbers. So the second point here is that I'm introducing this because sometimes in data science, it's very risky to work with, when you're dealing with random variables, to assume something is a discrete random variable when it's not, or something is a continuous random variable when it is not, or you're actually working with a particular kind of random variable, discrete random variable, but you do not know that that's a discrete random variable, and you're making the wrong assumptions. I always say this over and over again. If you make the wrong assumptions about data, it doesn't matter how impressive your analytics solution or approach is. You might have excellent analytics or machine learning, wrong answers. And the worst kind of getting wrong answers is not knowing that you got wrong answers. So when it comes to data science, never guess. I've said it over and over. Don't guess in data science. All right. Someone will tell me, I'm looking at the probability. I'm looking at the distribution. It looks like the whole thing is, we have some serious outliers. It looks like we're not getting the appropriate mean. It looks like there's some serious deviation, at a particular interval. It looks like this. I'm thinking maybe it's this. I'm not really sure what the problem is. Why not check the data distribution? Okay, stop guessing, because you have to make assumptions about data. So if you guess, you make an uncalculated assumption about the data, and you have to build your solutions based on assumptions. So if you have a wrong assumption and you build your solution based on that, you get the wrong results. But if you have the right assumptions or make the right assumptions based on understanding of the data itself, okay, the data itself is more important than the solution that you are trying to use to approach the problem. That's very important. So we're introducing all these details so that when you look at a particular set of outcomes or events, you'll be able to tell that this is a discrete random variable. Therefore, okay, what kind of discrete random variable? What kind of distribution functions would I be using for this random variable? So you have to know. Now, we have said this one here, but it turns out that this first line does not completely capture what a random variable can be. It assumes that you just have a finite number of possible values, just like the set we looked at. It's a finite set. All right. So I mentioned here that possible values can either constitute a finite set, like we have here, and um, like we have here. Sorry, like we have here. This is a finite set. This is a finite set. Of course, this one is continuous. This is finite. This is discrete. But we can also have something more interesting. We can have values that are members of a countably infinite sequence. Do you get? So I think we should call this a countably infinite sequence, because what we have here is like we are taking a range of values from 0.1 to 0.5. So it's not just a finite set like numbers like 5, 10, 7. It's an ordered sequence. You see that each one increases in steps of 0.1. Oh my God. I don't know. Is anybody really understand what I'm trying to say here?
Come again, please, sir.
This, this right here. Okay, let's go back. Discrete random variables can take in two types of values, right? Values that make up a finite set, or values that make up a countably infinite sequence, which means when we're dealing with discrete random variables, okay, the set we're looking at can either be a finite set or a countably infinite set. So we're looking at two things, finite and countably infinite. If we remove countably from here, what happens to an infinite sequence?
Becomes uncountable.
Infinite.
Yes, and that becomes a continuous random variable. So when we say countably infinite sequence, it means we have discretized this infinite sequence to countable values. So this set here is a countably infinite sequence, because normally you have this infinite sequence here from 0.1 to 0.5, okay? But when I discretize it and I say, okay, break this up into 5 parts, all right? Just break it up into 5 parts with spacings of 0.1 between them, all right? That's going to just, of course, if you say break this up into 5 parts, the spacing between them must be uniform. That's a countably infinite set. But let's say we have another set like this. Just a moment. So we have another set like 0.1, 0.2, 0.13, 0.7. Can you deduce any pattern here? Can you look at this and say this is a sequence? Remember what a sequence is? A sequence will follow a progression. Okay, Olawale says no. Anyone else agrees to that?
It's not a sequence.
Yes. So, but it's a finite set. So this will make up your discrete variable. It's a finite set, but it's not a sequence. The numbers are not sorted. They're not ordered. But this one is clearly a sequence. All right. It would have been an infinite set, as we would not break it up into exactly 5 parts. So we can count the number of parts we break it up into, aka we can count the number of elements. So this is a countably infinite sequence. All right. So once you have order between the elements, that if you break up a sequence and you have that sequence to be ordered and they follow a progression, like you notice that each element here increases by 0.1 until you get to 0.5. If you have such a sequence, okay, this kind of sequence is a countably infinite sequence, which is useful for us to work with random variables. So that's what we mean when we say it can either be a finite sequence or a countably infinite sequence. So that you know, not when you look at a sequence and you feel like, now this is a continuous variable, continuous random variable. You know, if you make that assumption, you're already set up for failure in that project, and that project, a lot of investments could have been made into that project, and so you don't want to do anything that will cost you any business value, cost the business value, and probably if it's too severe, maybe even cost you your job. All right. So continuous random variables, on the other hand, we have a random variable that has a continuum of possible values. What we mean by continuum means it's a set that spans all possible values infinitely within that range. So the continuous random variable, the values you have in that variable can just be an interval within R. Of course, you know that R is your infinite set of real numbers. So any interval within R, okay, is a continuous interval, and such a continuous interval would constitute or will make up values in a random variable, in a continuous random variable, sorry. So that's very important. So note these differences, because it's from here we now branch out the notion of probability distributions. This one leads to discrete probability distributions, okay, and this one leads to what? This one leads to continuous probability distributions. Now let me explain what I mean on this second line, just like I did here. because the first point captures it, but it's not very exhaustive. So the second point, one thing you will check to know that this is a continuous random variables. There are two possibilities. It could just be all numbers in a single interval, which means a continuum of possible values. So the values in a continuous random variable can just be all the numbers in a single interval in your real line. But it could also be all numbers in a disjoint union of such intervals. Okay, so just to make sure that you understand that, I'm going to quickly copy this out. Um, so we have two possibilities here. Possible values constitute. So let me just let me call this continuous random variables. Random variables. So possible values constitute either all numbers in a single interval in R or all numbers in a disjoint union of such intervals. This one is quite easy to understand. Just any possible interval in R, including all of R. Okay, you can have the entire set R, all the numbers in that set can make up your continuous random variable. But there'll be just too many outcomes. Then members in a disjoint union, all the members in a disjoint union of such intervals. So let's say we take the interval on this real line. We take the interval from, let's use what we're familiar with already, 0.1 to 0.5. All right, let's say we take this interval. Okay. Now we do a union. Let me put this in equation. All right. So we now do a union. Where's that? We do this union here. Of another interval. Let's call this one 2,7. Now, this is an interval in the real line. This is an interval also in the real line. Possible values of the continuous random variable can be all the members in this interval. All right, which means all the infinitely many numbers here and infinitely many numbers here. You can consider either all of the numbers or maybe you just pull out certain numbers. Okay, now when you say in a disjoint union of such intervals, what that simply means is that we're going to have a union of two sets that do not overlap, which means between these two sets, they are not going to be intersections. So we cannot have something like maybe 0.2 to 0.7. Why? Because already everything from 0.2 to 0. Maybe 69999. So sorry, 0.5. Everything from 0.2 to 0.5. Okay, in this set, they are going to be found in this set. So this is not really going to make sense. So disjoint simply means for the two sets, okay, the two sets that we have, when we take their union, there's no overlap between them. And so a continuous random variable can take values in this bigger set. Of course, this set is still a subset of this, but definitely a superset of those two intervals. A superset means, look here, I'm housing the both of you. Okay, so I contain the both of you. Both of you are sets. I'm also a set containing the both of you. So I'm a superset. All right. So, and of course, R is a superset of all the sets. Okay, so these are subsets of R and so on and so forth. So this entire set here, or this entire interval, is a disjoint union of two intervals. Of course, you can have more than two intervals that are going to be more than two disjoint intervals that you take their union, and then that will form the range of values you'll be considering for your continuous random variable. All right. Cool. Any questions so far before we proceed? Any questions? And sometimes your questions can also lead us to unravel some hidden details which would have otherwise gone unnoticed. All right, so two types of random variables: discrete random variables and continuous random variables. Okay, so I'm going to ask a question. Victoria, better girl. So what can you tell me is the difference between discrete random variables
Oh my god.
and continuous random variables?
I was just about to type that. I don't really understand, but I guess maybe when I watch it again. Because
It's
I
better
wanted to
you
ask
ask
you, because I
here
wanted to
because
ask you,
okay.
when you were explaining discrete random variables, I just wanted to confirm what I think you were saying, that like 0.1 comma 0.5 is like a yeah,
Which one?
this,
This?
yes, is this
Okay.
one like a is it continuous infinite? This one is like a continuous discrete, and then if you now break it down to 0.1 comma 0.2 up to 0.5 here, is that when it becomes a continuous infinite variable?
Wait, this is continuous. All right.
Okay.
Why is it continuous? Because we're looking at an interval represented by the curved brackets, which
Okay.
means we're taking all possible values between 0.1 and 0.5, but
Right.
0.1 and 0.5 are excluded.
Excluded.
All right, so it's continuous. There's nothing discrete about it. Okay.
Okay.
But let's say, and I want to say, okay, um, how do I put this? Okay, let's make it practical. All right, because I'm talking a lot of, sometimes when you are dealing with the mathematics of data science, you want to focus on the mathematics of data science. Then when you come back to practical data science, you know, to the practical data science. So let's make a practical data science analogy to drive this home. All right. So you have observed data, right? And in that observed data, there are maybe you have a sample of up to 1 million Nigerians, and you have records for different things about those 1 million Nigerians. All right. Of course, 1 million is not infinite, but it is large. Now, if you want to visualize something and you want to have that 1 million, you want to have those 1 million records, and maybe your x-axis, you're going to be having a problem of so many numbers. So instead of, how can you possibly on your graph? Let me do this here. Okay, so I'll just insert. Okay, I need a chart. Okay, so let's look at something suitable like okay, let's probably use a histogram. So I'm going to use this. All right.
Yeah.
Now, this is your histogram. Oh my god, I don't need this. Just a second. So this shift can be very unwieldy. I should probably put this on a new page. So you have your histogram like this, but the values you are looking at originally on the x-axis, we're going to have from 0 to 1 million. How can you possibly stack 0 to 1 million on your x-axis? So for each one, for point number 1, you check the value on the y-axis. You know, maybe you're not really trying to do a histogram. So this could be another chart, like a line chart. So forget about this being a histogram. I'll come back to the notion of histograms. But let's say we're starting with a line chart. So what you have is just a line that connects the x-axis to the y-axis. So for each value in the x-axis, you just draw the line and draw up to the line and check the value on the y-axis.
Right.
Is it not?
Yeah.
All right. So how can you possibly label this x-axis from 0 to 1 million? Is that
It's not
realistic?
practical. Yeah.
Yes. Even though you can force a program language to stack up all the values together, you're going to be having overlaps. In fact, it's going to be unwieldy. It's not practical. Okay, it's not practical for visual purposes and analytical purposes. So instead, we say, okay, let's not be too naive here. Let us import a solid understanding of dealing with data distributions. So instead of labeling this x-axis from 0 to 1 million, I say let me discretize. All right. So instead of having a line chart, I'm going to have a histogram. The first bin in the histogram, all right, how do I put this? You would discretize that set of values to a specific number of bins. Here we have 6 bins: 1, 2, 3, 4, 5, 6. It could be 10, it could be 20, depending on what you really want. All right. So we'll say each bins, of course, have equal width. So let's break up those 1 million values into ranges, so that the first bin can be 0 to maybe 20,000 or 50,000. If you use 50,000, by the time you do that 20 times, you get to 1 million, is it not? So 0 to 50,000, all the people that fell within that range of 0 to 50,000 would check the distribution for them. 50,000 are one, so 100,000 will be the second bin, and so on. So we are discretizing them into equal sets of numbers or equal ranges of numbers. So we've had a number that was, terribly large. We've now discretized it. All right. Possibly, maybe that 1 to 1 million was even an infinite set. It's even possible you have a continuous, maybe you're dealing with a continuous random variable like price. Okay, normally you should have that on the y-axis, but let's say we're having that on the x-axis. So if you have a price variable that takes values from 0 to 1 million, obviously that's a continuous variable. So you can't, that is continuous, and to do a histogram like this, you need to change that from continuous data to discrete data, and you achieve that by breaking it up into discrete ranges. So essentially what we've achieved here is to split up an otherwise infinite sequence into a discrete sequence with a specified number of elements, each element having the same number of spacing between them. This one is not like this. This one is completely finite because there's no specific order, there's no specific base spacing between them. It's just arbitrary values just being added to the set. So this is a finite set, but this is a countably infinite set, which now can be used for a discrete random variable. So when I break up 0 to 1 million into 20 bins of ranges from 0 to 50,000, all right, bins of 50,000 elements, okay, I've converted an infinite set to a countably infinite set, and that countably infinite set is a discrete set. I hope that makes sense.
Yeah.
Yeah,
It
it
makes
makes
sense.
sense. It makes sense.
Victoria doesn't seem like she needs further explanation. So
It actually
where do
makes
you
sense.
it does? Okay, so let's proceed. So that's what you have for discrete random variables. It could be two ways. It could be a finite set. It could be a previously continuous set or infinite set or sequence, which you now discretize by breaking it up into countable elements. So you can count the number of elements in that sequence now. It's no longer uncountable. Price data is uncountable because you can have, even between $0 and $100, we have infinite number of values. Okay, but if we now want to work with certain kinds of visual distributions, if we want to visualize certain distributions, and we say, okay, let's use a histogram. Maybe there's something we really need to check. So let's try to use a histogram. Of course, a histogram, and for a histogram, we would have to discretize the numerical values. Remember that histogram work with numerical values, while bar charts work with categorical values. That is, at the x-axis, you have categorical values for bar charts and numerical values for histograms. But histograms, the numerical value you have for histograms is discrete numerical, discrete values, countable values. Does that make sense? Oh my god, time is fast spent. Okay,
Yeah, it does make sense.
let's finish up this. So now coming to probability distributions. All right, let's see how long we've spent here. We spent almost 1 hour 30 minutes. All right. So we have talked about random variables, right? Discrete and continuous. Now let's talk about probability distributions, which I've explained earlier. Okay, so a probability distribution is a data distribution that will consist of the possible values of a random variable and their corresponding probabilities, which means we're talking about experimental outcomes, and to each outcome or to each event, we assign probabilities. Remember that an event may not be a single outcome. An event may actually be a set of outcomes. So if we say, for example, in the roulette wheel case study, the event black or even is a set of so many outcomes. Okay, so some events are single outcomes, like the event that the ball will land in a 13, in the pocket, in the pocket that is number 13. That event that the ball landed there is a single outcome. But there are some events that can take all possible, so many possible number of outcomes, more than just one. So for each event in your experimental or your experimentation, as you assign the corresponding probabilities, the associations that is now formed make up your data distribution. So, and this data distribution or this probability distribution, has a notion of uncertainty. It tells you how uncertain the numerical outcomes are. So for event A, sales is going to be $2,000, but the probability for that is 0.1. Oh, you look at it and say, oh, that's too low. That's too low. So what do we really do here? Of course, you have to work with the other outcomes to make correct deductions. So the $2,000 and the 0.1 is a set in your probability distribution. And then, of course, you can visualize this distribution. But there's something about distribution I need to be very particular. So sorry, guys. I've been having a cough for a while because of the weather. All right. Thank you very much, Victoria. So, what was I saying? I need to be very particular about.
Okay.
Yeah, go ahead.
So you were saying that you wanted to mention something about distribution.
Yes. So I need to be very particular about distributions. Okay, this is very important. A distribution is first of all mathematical before it is visual. So most times when you think of distribution, you first think of visuals. Okay, the plot of a normal distribution, the plot of an exponential distribution, plot of a geometric distribution. These plots help us make sense of the distributions because numbers sometimes abstract a lot of things. Okay, but the visuals themselves are not the distributions. Those plots or visuals are visual representations of the distributions. As a data scientist, you must be able to separate, the notion of the actual distribution from its visual representation. I don't know if that makes sense.
Does.
Yeah, because I'm mentioning this because it's not something you hear so often, and people people tend to think that when you plot a normal distribution, that is the normal distribution. So it only shows you what the normal distribution looks like. It's not the normal distribution itself. It's only a visual representation of the normal distribution. And sometimes it's those visual representations you need to you need to use to make sense of certain kinds of data. Because when you see, for example, if you see a number like skewness is 0.45, you'll be wondering how asymmetric is this skewness. If you have been working with data for a long time and you are so used to different skewness values for different data distributions, the moment you see a particular value, any value between maybe 0.4 and 0.6, you can already in your mind, you can already begin to visualize what the lopsidedness will be. That is, where does it shift towards? Does it shift far from the mean on the right side, or does it shift far from the mean on the left side? Of course, if it's greater than 0, it will shift, towards the right. And then if it's less than 0, that's if it's a negative, it will shift towards the left. Okay, so when you look at a number, but sometimes it's not really easy to interpret those numbers. So visualizing them help okay. Then you also know the size of the tails of the distribution. Is it a fat tail? Is it a thin tail? Then you can also go to check the kurtosis of the data. Looking at the distribution, the visual of the distribution alone, you can interpret the kurtosis of the data. But the visual will not tell you the exact value of the kurtosis or the skewness or all that. So you still need to actually check the numerical values. So all these distributions are numerical stuff. Okay, they're not graphical stuff. They're not graphs. They're numerical. Okay, they're functions. Especially when we come back to probability distributions, you're dealing with functions that output values. Okay, your expectation or the central tendency of your data, we use expectation a lot when we're dealing with probability data or experimental data. So instead of saying mean, we just say, okay, the expectation of the data of the distribution. The expectation is a function, all right? The variance is a function, and so on and so forth. So the probability distribution, as I was saying, tells you how certain the outcomes are. And another thing I should mention is that they are not based on observed data, at least not directly. We can actually use observed data to run experiments. For example, just a second, I made a typo there. Based on observed data. All right. So it's not based on observed data, at least not directly, which means you're not really using an observed data set to create these probability distributions or to assign probabilities to observed data. No. You can still use the observed data to come up with. You can still use the. Hello. So, I can't hear me. Okay, I think I had a little network disruption. So you can use the observed data to maybe check relative frequencies, especially if you have a very voluminous data set. You can check relative frequencies. For example, financial data is usually very voluminous. Okay, data about stock prices or stock trading or crypto trading, data that you get from financial markets are also voluminous data. So we can just pull out certain things from those data and use that to guide experiments. But if you're doing a stock prediction, for example, it's going to be probabilistic, right? So I've not entered random versus continuous distributions. I'm going to tell you something about what makes continuous distributions more tricky than random distributions. So hopefully we're going to work with a random distribution example this night before we end this class. So we have discrete probability distributions and continuous probability distributions. Your discrete is simply I'm taking the distribution of a discrete random variable. So this is a discrete probability distribution. All right. So the values here usually result from a count. What that means is that, although not always a count, because like I mentioned earlier, sometimes your discrete random variable is taking values not just from a finite set, but sometimes from an infinitely infinite set. All right. So it can also come from a measurement, not just a count. Usually, measurement is continuous. When you are doing measurements, measurement of price, measurement of temperature, usually have continuous values. The devices or instruments we're using for those measurements, okay, will be taking in continuous data. All right. So measurement data is usually infinite. So for discrete probability distributions, we're talking about variable values that result from a count. But we can also use measurement data by doing what I explained earlier, which is discretizing the data into countable ranges, so that they reduce from a continuous set of values to a countable discrete set of values. And so these sets make up your discrete probability distributions. Then for continuous probability distribution, the values come from a continuous random variable, of course, and they usually result from measurements. In most cases, you're trying to measure something. For example, the measurement could be, what is salary of data scientists in Nigeria? Okay, so trust me, it's not something I want to talk about here because it's not competitive at an international scale. So, I mean, international values, you'll see values from from most cases like $40,000 to stuff as much as $120,000. And then of course, you know that there are different levels of data scientists. When you start out, entry level, you're like a junior data scientist. Your salary may be like that kind of $40,000. You know that's just gross. They'll still take away tax and other things. So maybe you'll be ending up with 25,000 or something like that. But then compare $25,000 to what you earn here and think you are earning a lot. You know that it makes you just really want to start get angry and leave the setting. Which is what we expect. Want you guys to start getting opportunities at the international scale. Even if you don't want to go into full-time data science, like being on a job, there's also the consulting space, also very rich and very large. It's very, what's it called? The consulting space is very valuable as well. So if you don't want to go into a data job, if a 9 to 5 or something like that, or a remote job, of course, consulting also exposes you to deep business knowledge about data science, which you might not get on the job. All right, back to what we're talking about, salaries. So there are different levels to a data scientist. You enter junior data scientist, then maybe after 1 year, depending on your speed, for some it takes 2 years, you get into the data science role itself, where you now realize that data science is a world on its own, and it's not all the conventional things you learned in a boot camp, and you now need to be very pragmatic and also have very strong understanding of how to deal with any kind of data. And then after maybe this role can take like 4 or 5 years or more, depending. Can be on a data scientist role for like 12 years. So then from there, you move up the ladder a little, senior data scientist. These guys now, their salary, of course, is over $100,000, depending on the environment and the size of the organization. If it's Google, oh my God, it's a lot of money. Okay, so then from senior data scientists, you're already talking about, okay, we have reached a level now where we are, how do I put this? Um, you are going to be responsible for specific data products. All right. So you would be working less with teams, but you might be supervising other data scientists. But then you would probably be assigned a particular product in the company's data value stream, and then you need to work with that. All right. Then from there, in environments like Google, you now have some promotions from senior data scientists, like staff data scientists. The staff data scientist is like, at this level, you are a data science expert. You are an authority in this field. All right, so you don't need to do so much. Just come to the office, and we're going to be paying you. But of course, you'll be handling critical components of business decisions with data, and stuff that your senior data scientist cannot handle. It comes to you. So environments like Google and all that, of course, you should be talking about something approaching $1 million for all the staff that data scientists. It's still an estimate because these are estimated values you see. So we cannot say this is exactly what it is. So these values are quite large. In Nigeria, if you're a senior data scientist, um, let's not talk about this. So it's not encouraging. So from the Nigerian setting, it looks like it's much or it's huge. But as you rise in your career and of course as you advance in life, responsibilities increase. And so what you look at when you're younger as a high value, you begin to see that this is not so much of money. When I was a teenager, I thought 1 million was a lot of money until I made my first million. And when I handled the money, I just saw how small it really was. So as you get to those levels, it's like those things now begin to get smaller. They don't look as huge as they were before. Of course, your financial taste increases as well, and all that. So I'm talking about staff data scientists, and they begin to earn close to millions of dollars. Then in Google, you have the final promotion. If you're not going to go into management or executive roles, okay, there are some roles that are like equivalent to C-suite, but they are like executive roles. So instead of making you maybe a chief information officer or something like that, maybe you're more of a technical person than a strategy person, but you've pulled a lot of years of experience and expertise, and they need to promote you. Then Google has roles like distinguished scientists. That's like I think the highest. Then at Google at the moment, I think I'm familiar with two guys who got to distinguished scientists, which was like the highest for everyone in technical roles. But these two guys became more distinguished than distinguished scientists, so they created new roles for them. I think two guys, I can't remember the details again. They created new roles for them and called them fellow data scientists. So these guys are of course, getting millions of dollars in a year. But the interesting thing about these roles is that they're also the educational requirement for them is also really high. So you won't see a distinguished data scientist or AI researcher at AI that doesn't have the highest level of educational background. So let's say we have data that now uh, um, gets tries to get the salaries of each of these individuals at the various levels. All right, so you have that column. So the measurement now, okay, you would call that you call it a continuous data, all right, because the measurement are not discrete values, all right. They're neither other discrete values or on other discrete values. You can't discretize it like that. You can have, you know, the numbers taking any value from the real line. You can have someone earning $100,000, another person on earning $100,999. So sometimes you see some of these numbers with decimal points. Of course, when you calculate tax and all those things, we're ending up with decimal points. So that's salary data now is going to be continuous data. So it results from measurements, which means you went about to obtain the values of more or less like to measure. You're trying to measure salaries, of course, by asking questions. Okay, so you ask questions like, how much salary are you getting or are you making? The person might not tell you the exact. They might just give an estimate. I say, okay, estimated is like this. So, more or less like you're measuring. And so you use different instruments for that, survey data, observational studies, and all of that. So this kind of data is what makes up a continuous random variable, which of course gives you your continuous probability distribution. So let's now quickly move to summary measures for probability distributions. I've actually talked about these summary measures in one of our previous sessions when we introduced probability, but that session that I mentioned was not recorded. So I need to now go over the details again. The way you work with observed data to take a mean and all that is going to be very different when you're dealing with data where each row, okay, has like two elements. The what's it called? The value of the outcome and the probability that that outcome would occur. So instead of dividing that value by maybe summing all the values in the data and dividing by the number of values to get the mean, we use a different approach. And then the symbols are also quite different, especially for the mean. We use, of course, notation changes depending on the material or the people you're working with. But one thing is you should be able to look at the letter there and know that you're talking about a mean here. All right. I hope you guys are with me. Don't worry, we are already almost done with this. Once we finish up this, we move straight to a simple example. Now, you have the mean here. The mean is simply for each set we have, multiply for each record or each event in the random variable, multiply the value of the outcome by the probability of occurrence of that outcome. So we usually represent probabilities in two ways. I think I might have closed my. Okay, it's here. So we usually represent probabilities in two ways. Let me delete that. So the probability of a random variable, of the element in a random variable, can look like this. You can actually have something like this. Don't worry, it's not so much of a tricky notion. So P, what this simply means is the probability of X where the value is X. All right, we can write that as the probability for a specific record in the data. Of course, we can put this in subscript. Put that, introduce a subscript and call this I. So the probability of X when X is element 1, give me the value for that. So maybe to do this, I'm going to bring up that data we've been working with earlier. The table we worked with earlier. So let's bring up this. So the probability of X equals Xi, which means I takes in values from 1 to the number of elements we have. All right, so if we have k number of events, I would take values from 1 to k. All right, so 1 is the first record, 2 is the second record, and k is the kth record. And k could be any number, like it could be the 15th record, the 20th record, and so on. Now, for the first record, okay, we can now rewrite this as probability. The probability that X is, we can write this as x1, or you can simply say the probability that X is 2000. What's the probability there? What's the probability of this? Yes, anyone? I hope you guys have not disappeared from the meeting. How many of you are still here? Okay. All right, so my question is, what's the probability that X is 2000? Because when we write this, we're simply saying the probability that X is, when we say Xi, the I represents or generalizes all the events. So I can take in value from 1. So x1 means the first records or the first event. So what's the probability that x is that first event, which means x is 2000? What's the probability value that we're going to have there?
1/2000.
I'm sorry, I didn't get that.
1/2000.
I can't hear you.
2000.
It's going to be 2000. That's this, right?
I said 1 divided by 2000.
What do I do? What? Can you type the question so that I know what you're talking about? I can't hear you clearly.
Oh, sorry. I said 1 divided by 2000.
Oh, okay. 1 divided by 2000.
Can you hear me now?
All right. I can hear you now. 1 divided by 2000. Is this what you
Yeah,
mean?
exactly. This.
Okay.
But
Why
I
is it
can't
1
hear
divided by
you.
2000?
Let me fix this thing.
Does anyone else have a different value for that probability? Okay, and then it says 0.101 times 2000. So which one are we going to go for? 1 over 2000, 0.01 times 2000. Anyone else? Now, we have to be very careful here. The probability that x is x1 is simply, this is the x1. This guy here is the outcome. All right? This is the outcome. This is the probability of this outcome. So the probability is 2000 is 0.01. Just give me the probability value you have there. No multiplication, no division, nothing. This is x1, the outcome, the probability of the outcome. So your capital X is a random variable, which in this case is sales, and your x1 is the outcome in the first event. All right, the outcome here is x1. So the probability that sales is 2000 is 0.01. So instead of using this notation, we use capital P here because we're trying to, and this is the full version, and we're trying to, we have capital X representing the variable. So we're simply saying, what is the probability of X, but narrow it down to where you have 2000. So you cannot use small p to talk about the probability of big X. All right. But when you're dealing directly with small x, we can simply say, okay, give me the probability of x1. This is the same as this. Probability of x1 simply means go to x1, which is here. What's the probability of this guy? The answer is this guy. So the answer here is 0.01. All right. Now, this gives you, that result, and that's the probability you have here. This notation is like a simplification of this notation. All right, so we can use this notation to represent that. This is the exact notation. Okay, but practically, when writing or typing or any of that, you just really use this one because it's faster to write up. So the probability that x is x2 is going to be what? We're going to have x2 here. So what's the probability that x is x2?
Point 0.07.
Yes, thank you very much. 0.07. That's the probability we have there. And all this gives us, we can now check for all the other values we have. As long as these are filled, we can check the probabilities. So we can use this notation or that notation. So if you see any of the notations, just know what you're dealing with. So here we just use the small p and small xi to represent each of these. All right. So we can get the mean by multiplying for each one. For each record, we multiply the outcome by the number, by the probability, sorry. All right, so we do that for here, we do that for here. Then we sum all the products. The summation of the products for each individual outcome and their corresponding probabilities, from I to the final value k, the final event k, that gives you the expectation of x, aka the mean. So when you're dealing with probability, you're working with probabilities and generating experimental samples. We don't use the conventional sample mean, sample variance for observed data. These are the, the things we use. So let me pull up my okay. Let's use all right, guys. Sorry for that delay. So we want to look at a case study where um, we'll be solving this problem, okay, and we'll compute summary statistics for that probability distribution. If time permits, we'll try to visualize the distribution. Of course, it's a small distribution, but we can still work with it. So, who can read for us? I just want to be sure you guys are with me, so I'm taking a volunteer to read what's on the
I'll read.
slide. Okay, go ahead, please.
Okay. An investor is concerned with the market return for the coming year, where the market return is defined as the percentage gain or loss if negative over the year. There are five possible scenarios for the national economy in the coming year: rapid expansion, moderate expansion, no growth, moderate contraction, and serious contraction. Furthermore, she has used all of the information available to her to estimate that the market returns for these scenarios are respectively 23%, 18%, 15%, 9%, and 3%. Returns vary from a high of 23% to a low of 3%. Also, she has assessed that the probabilities of these outcomes are 0.12, 0.40, 0.25, 0.15, and 0.08 to describe the probability distribution of the market return. Compute the
All right, thank you very much.
okay.
Okay, yeah, go ahead.
Okay, to compute the mean, variance, and standard deviation of the probability distribution of the market return.
Okay, so our objective, it's a pretty long question, so I'll just copy this and put it in Markdown on Jupyter Notebook, on Jupyter Lab. So we're going to just put this here.